Injection molding is the most common method for mass manufacturing of products. Examples include the manufacturing of precision devices, instrument panels, seats, and other plastic fittings. It is a complex thermodynamic process with constant changes in pressure, temperature, and flow of the mold material. Several types of defects happen on the production line, such as burn marks, blisters, or surface irregularities due to changes in the thermodynamic environment. Our Smart Quality as a Service platform provides real-time sense and response capabilities to the injection molding system. SQAAS is capable of analyzing data in real time and selecting the right model for defect prediction on the assembly line and preventive maintenance. So how does Amplo Global really do it? Here we will demo a use case for an application of SQAAS in injection molding of automotive parts. We start by contextualizing the data to the machine components and map the data captured from the sensors to the injection molding process. We then filter out the imperfections or abnormalities to clean the data and feed it into the machine learning model. Once we have clean, normalized data, we select the appropriate feature set by identifying data fields that show variations based on defects in the mold. We then run the selected features through multiple data modeling algorithms, and out of those, we pick the one that falls under the most acceptable defect misclassification rate. Defect misclassification is key, and we define it as the proportion of false positives and false negatives in relation to the total data set. In this particular case, both the Logistic Regression and Gaussian NB models show high false positives. The K-Neighbours model shows a lower defect misclassification rate. The best result we get is with the decision tree model with a zero defect misclassification. We now see on the left the entire decision tree built by traversing all the nodes, and on the right we have a magnified view of a part of that decision tree model. We can see how the recursive nature of the features within the injection molding cycles cause a natural alignment to the physical phenomena. To help us understand how the thermodynamic parameters such as injection temperature, cushion size, cycle time, etc. relate to each other, SQAAS uses correlation heat maps. Correlation heat maps show strong distortions on the impact strength of correlated features. We further analyze the correlation between the fields of pressure, flow, and temperature inside the mold. The presence of a light yellow to green shade shows the existence of a medium to strong correlation. After adjusting for the effects of correlation, we look at the feature importance chart, which indicates that the attribute cushion size is the most significantly contributing factor which leads to defects in the molds. We also apply the model to predict defects with live data streaming from embedded sensors. What happens at the plant floor is visible through the SQAAS platform, which provides real-time updates to KPI dashboards. Real-time data helps to build the threshold levels and an early warning system. SQAAS provides actionable insights like machines showing a higher number of defects, cycle time anomalies, and also raw material issues that can impact the overall equipment efficiency and overall plant productivity.